Okay, so now we're going to start doing some calculations with equilibrium, and that's where it kind of gets a little tough. So just a reminder, chemical reactions can go in either to products or reactants depending on the conditions if they're reversible. Remember, we're going to see these double arrow things. When they establish a dynamic equilibrium, it's the point at which the rate of the forward reaction equals the rate in reverse, and the number of molecules changing to products equals the number changing back to reactants. And they're constantly changing motion, but they're not increasing the net amount. That's not changing. It doesn't mean the concentrations are equal either. Okay, very likely the concentrations are not equal. In chemical equilibrium, the concentrations remain the same under those conditions until you change the conditions, then Le Chatelier's principle applies. Every reversible reaction proceeds to an equilibrium state that can be described by a specific equilibrium constant. It's called KEQ. That's kind of the generic term. Equilibrium means balanced, where the rate forward equals the rate in reverse. The equilibrium constant is a way to determine how much of the reaction goes to completion. It's a way of calculating that. So, like I mentioned earlier, gasoline burning goes 100% to completion, but many of these reactions don't. And so, based on the value of the KEQ, you can determine how much of it goes to completion. So, for any reversible reaction, the way you set up KEQ to calculate it is it's the products raised to a coefficient multiplied by the next product raised to its coefficient divided by the reactant raised to its coefficient multiplied by the next reactant raised to its coefficient. There are plus signs in the equation, but they become multiplication signs inside KEQ. Concentration is the bracket thing. It means molarity. And what it means, if it's significantly greater than 1, that means that there's way more product than there is reactant. It's almost completion, going to completion. Products are favored. That's the term that they use to describe it. And the equilibrium lies on the right side of the arrow. If it's significantly less than 1, that means the equilibrium lies to the left. You have a lot more reactants than you do products. It doesn't even really start going. It just kind of stays there. And the reactants are favored. If the KQ is about 1, then it's about an equal amount of reactants and products. That doesn't happen very often. Okay. Homogeneous equilibrium is where everything is one state of matter. We're only going to deal with aqueous or gaseous. If it involves solids and liquids, we're not going to include them. Only gases and aqueous solutions go into KQ because solids and liquids don't change very much at equilibrium. So we just leave them out. It affects the math too much. So let's practice writing some equilibrium expressions. So this one, I'm going to identify my products as NH3. So KEQ equals the concentration of NH3 squared, because it has a 2, over N2 raised to the power of 1 multiplied times hydrogen cubed, because it has a coefficient of 3. Products over reactants. If I was to do this one, I'm going to do my products again. KEQ is HI squared, because it has a coefficient of 2, over H2 to the first power. But notice I'm not going to include that because it is a solid. That is my equilibrium expression. Solids are not included. This one, KEQ, is the product NO2, 4th power, multiplied times water, which is a gas here, so it counts. It's a 6th power, over NH3 to the 4th power, and oxygen to the 7th power. Kind of a complicated setup. So now we're going to calculate KEQ. So we're going to use the KEQ we had before, which is NH3 and H3 squared over N2 times H2 cubed. And notice I'm writing, this is called the equilibrium expression. I'm going to write that down, and then I'm going to plug in the numbers. NH3 is 3 squared over 1 for the N2 and 2 cubed. What I have is 9 over 8. And I get 1.125. In terms of sig figs, I would just go with that and call it 1.1. The other thing that's very cool about KEQ, some of you will appreciate, is that units are not included because the units change every time. So you don't have to worry about the units. So 1.1 is my value and I'm done. Okay, let me erase this. I'm not sure why that's still there. All right, using the KEQ expression, now we're going to calculate it for a different way. So we still have the expression KEQ is NH3 squared over N2 times H2 cubed. That's the expression, and I would recommend writing it down. KEQ is 25, so I'm going to put a 25 in there. NH3 is 4, and it gets squared. H2 is 2, and it gets cubed. And this is x. So you have to do a little bit of algebra. So what I have is 25 over 1 equals 16 over x times 8. However you want to do this, I would just cross multiply. And I get 16 equals 200x divided by 200. And you get 0.08. And the units for this will have a unit because we're solving for a concentration, 0.08. And here's another thing you can do. You should put that number back in and see if it works. I mean, it should be close. So if I do 4 squared divided by 0.08 divided by 8, bingo, 25. Okay. So now we're going to find the NH3. Again, I'm going to write down the KEQ expression. NH3 squared over N2 H2 cubed. KEQ is given to me. 0.0055 equals, I don't know what the NH3 is, x, but it has to be squared because it's squared in the expression. And the N2 is 3 times 2 cubed. So what I end up with is 0.0055 over 1 equals x squared over 24. And again, I'm going to cross multiply. (0.132), take the square root. 0.36 molarity equals x. And again, you are solving for a concentration, and concentrations have units. K's don't.